The purpose of this presentation is to discuss mathematically different ways of comparing chemical shift tensors. For example, tensors that you get from experimental methods or theory versus experiment, for example. And I want to talk about a method called the icosahedral representation. Of course, the way we do structural studies with NMR is continuously evolving, and in solids, dipole coupling has come to dominate structural studies. But increasingly, chemical shift tensors are being used to derive structures. The first structures from shift tensors was done in 1995, and in the intervening 10 years, only 6 structures were solved using shift tensors. But from 2005 to 2014, over 20 structures were solved, so it's becoming an increasingly important way to solve structure and might become one that's very important in the future. A summary of the data that I've shown here in the graph is given in ChemPhys in a paper that will come out shortly. Before we talk about ways to compare the chemical shift tensor, I want to talk about what the shift tensor is. Chemical shift is represented by this 3x3 matrix with 6 components. There are only 6 because the off-diagonal elements are equivalent. So delta xy equals delta yx, for example. To get all 6 components for a single molecular site, you usually require large single crystals. An important alternative is to think about it diagonalizing the tensor. So we take the off-diagonal elements and we put the intensity on the diagonal. These are called the chemical shift tensor principal values, and they're different than the full tensor in that we can actually obtain all these values for microcrystalline powders. When we diagonalize the matrix, we usually lose information on orientation, so we don't know which is the x, y, and z direction. So we typically don't call them delta xx, delta yy, and delta zz. We list them serially, delta 1, 1, delta 2, 2, and 3, 3, with 1, 1 being larger than 2, 2, which is larger than 3, 3. So we just order them by magnitude. The isotropic shift, which you're probably more used to seeing in liquids, for example, is derived from the principal values. It's just the average of the 3 principal values. The way the principal values are derived experimentally can be seen from this line shape. This is for a single site like the carbon and calcium formate, for example. And it gives a strange line shape. And the reason why is that chemical shift varies with orientation. So if you have a powder, you have all orientations and you get them populating this large region. And you just read the principal values off as the left side, the middle, and the right side. And the 2, 2 component can vary all the way from over on the 1, 1 to degenerate with 3, 3 and everything in between. So there's a lot of strange line shapes you get out of here. Typically we don't see a powder pattern like this though, we actually see this kind of a shape, and that's because most measurements involve sample spinning. And when we spin, we separate the powder pattern into a series of narrow lines separated by the spinning speed, and these are called spinning sidebands, and this is what we typically observe in tensor measurement experiments. The earlier work on the chemical shift tensor was focused heavily on developing pulse sequence methodology for doing the analysis. So from about 1983 till about 2006, and since then also, but much less, methodology was the focus, pulse sequence development. Most of the methods that have been developed display data in this manner, with isotropic shift shown on the one axis and powder patterns for each resonance shown in the second dimension. So here's an example with a small carbohydrate that has 6 different forms simultaneously present in the solid state that are exchanging on the kilohertz time scale. And for just one single site, we can actually think of getting lines for each of the 6 different shapes and powder patterns for all 6. And even though a large variety of experiments have been explored over the years, time and experience have sort of sorted out which ones are more easily implemented and more widely usable. And at present, most of the experimental tensor principal values that have been published have been obtained by one of 6 different methods or types of methods. One type is slow spinning, and we just spin slowly and get the sideband pattern that I just illustrated. And then we derive principal values from that. The magic angle turning methods, or MAT methods, are one of the more widely used ones. It's MAT and format. 2D pass is also another slow spinning method that's widely used. An alternative approach is to spin fast and get rid of all the side bends, and then use pulses to actually reintroduce the sidebands. And those are called CSA recoupling experiments. The family of CSA amplification experiments is one example. Super is another method that gives individual powder patterns without sidebands for each resonance. And RAI is a third method of CSA recoupling. And like I said, all these 2D experiments provide a 1D spectrum with one line per resonance on the one axis, and powder patterns for each resonance on the second dimension. Recently, work has shifted away from doing methodology development to applications. Can we get structure, including crystal structure, from shift tensors? The problem with this is when we do a measurement, we actually get a lot of tensor values, and we don't know what it means in terms of structure, so we have to find a way to correlate the two. And there are very few known empirical relationships relating tensor data to structure. So the method people have come up with is actually building a lot of structures on a computer, then calculating the tensors for each model structure theoretically, and then finding where they get agreement with the experiment. For example, the first structure done was this small fungal product from Papua New Guinea. And since it's small, we can actually think of building all possible stereochemistry and conformational possibilities. And when this was done, we had about 200 model structures, and we were able to derive the correct stereochemistry and conformation for this. So if we're going to compare experimental and theoretical data, the question is there a best way to do this? And the answer is mathematically yes. There is a method described by Don Alderman, Mark Sherwood, and Dave Grant in 1993, and it calculates a metric called distance between the two functions, and it's given by this expression here. This expression requires that we get equations for f and g. So, for example, f might be the shift tensor from one experimental method, and g might be from another, or maybe from theory and experiment. So we're two things we're calculating that are the same thing, but we obtain different ways. And since shift varies with the field, we can think of writing an expression we can use. If we talk about the tensor being projected along the different direction cosines, we can get this expression here. And it's just, the c's represent the cosines just for shorthand. And this is a function that tells us what the shift does in terms of orientation. We can write this more simply as this sum of 6 terms. And we can think of putting this in the equation. We also have to have an expression for the other experimental method or the theory. And this is what we call g in the equation. And if we get a similar expression, but now call it epsilon rather than delta for the tensors that are derived from the different method or the theory, we can get all the terms we need to solve the expression for distance. And so, like I said, if we assume f is experimental data and g is computed values, or f is experimental data from one experiment, g is experimental data from another experiment, we can actually put it into the expression for d and solve it. And what we find is that we get, when we do all the math, we come up with this expression here. It just takes the difference between the two different tensor values. And then we have this term in the middle that only involves direction cosine matrices. So we can actually solve this and get a number out for each term. There's, in Cartesian space, or there's 36 terms for all the directions. And if we do the math, we come up with these numbers. So we can think of now we have something that we can put in this d squared equation that we showed initially and get an equation out. So if we do it for full tensors, all 6 components, and we do the math, here's what the distance comes out to be. We just put in the delta for one method and epsilon from another method or from theory, and we do the math, and we can get a distance out. If we have only chemical shift tensor values, 3 shifts for every nucleus, the math becomes a little simpler, some of the terms drop out, and here's the expression we would use if you go through the math. This will give us the distance between comparing theory and experiment, for example. The problem with this approach is that when we calculate shifts using a theoretical method, we don't get shifts, we get shieldings. And those have to be converted into shifts to do a comparison. The d squared, the distance formula, requires shifts. Typically what people do is they say, well, I know that the calculated shift and the experimental shift are strongly correlated, so I can just plot them versus each other and then fit it to a least squares linear fit and get an equation that tells me how to convert theory into experimental data. So I convert theoretical shieldings into theoretical shifts this way. This is actually only appropriate when there's, all data are equally weighted and uncorrelated. And you can see it when the distance metric that we showed in Cartesian space actually has the x, x, y, y, and z term have off-diagonal non-zero elements, so there's correlation between terms. So in fact, just plotting them and fitting a straight line to it is actually not correct, and we have to think of another way to do it. Well, if we say that the chemical shift tensor represents the shift in 6 different orientations of space that are equally spaced from each other, one of the ideas is we can say, well, is there a shape that actually has 6 unique axes that are equally spaced? And the icosahedron is such a shape. It has 6 equally spaced axes, so it naturally is a representation for a second-rank tensor. So we can think of evaluating distances and getting the distance metric for a icosahedral space. And if we actually go through this in terms of the math, we can get a distance metric, and it's here. And now what you see, all the elements are equally weighted, and there are no correlation between terms. So this is actually an appropriate way to do it, and it does give a very simple expression for the distance. It's just the difference between corresponding components from theory and experiment, or 2 different experimental methods, squared, add them up and take the average. If we have principal values, we don't have 6 components, we only have 3. So the equation becomes a little simpler for just principal values, and it's given by 3D here. So it's quite a simple approach. If we actually can convert everything into icosahedral space and do the analysis there, we get a little simpler way to compare distances. So what I want to talk about right now is a recipe for how to do that. How do we actually get everything into this icosahedral representation and do the comparison? And this is just a formula that you can follow to get it to work. The first step is we have to convert both experimental data and theoretical shifts into the icosahedral representation. And here's the way we do it. We get a first expression, which is chi1, and it mixes the delta 1, 1 and the delta 2, 2. And then we can think of getting another term, so we get mix 2, 2 and 3, 3. And then we mix 3, 3 and 1, 1. And we get chi1, chi2, and chi3 rather than delta 1, 1, delta 2, 2, and delta 3, 3. So it's the same thing, it's just now in the icosahedral representation. And now, it is appropriate to do a least squares fit to a line. So we can plot icosahedral shifts as the x values, icosahedral shieldings as the y values, and then we fit it to a least squares line. And we get an equation that prescribes how to convert theoretical shieldings into theoretical shifts, but both in the icosahedral representation. If we can do that, now we can compare experimental data with potentially hundreds of theoretical models and get d squared for each and choose the minimum as our best structure. One of the problems with this approach is now we have, when we're done with it all, we want to report values experimentally for the principal values, and we also want to report the best model structure. But now the model that we have is actually in icosahedral space. So we have to do one more step before we're done. We have to convert the model, the best model, back into the Cartesian representation. So when we report experimental and theoretical data, they're both in Cartesian space. And if you look at this expression that we had for converting from Cartesian space to icosahedral, all we do is reverse this. So you can think of splitting this up into a design matrix, this a squared, b squared, Cartesian space, which is delta, icosahedral space, which is chi. And we can write it more generally like chi equals a times delta, and then we just solve for delta. The design matrix is a square matrix, so we can take the inverse of it. We multiply both sides by the inverse, and we come up with delta. Now this is what we want. Theoretical values appropriately scaled using the slope and intercept we got from a equally weighted, uncorrelated distance metric, and now converted back into Cartesian shifts. There is one problem with doing this comparison this way, and that is d squared is biased in favor of the incorrect structures. So one of the assumptions that you make when you do this comparison is that all the things you're comparing share the same orientation of the principal axis system, the axes along which we're measuring shielding. This is only going to be true for the correct structure. For the incorrect structure, it can be a really bad assumption. Some of the incorrect structures can have really very different orientations. And so we're actually making an assumption that is biased in favor of incorrect structures. So it's tempting to think this isn't going to work. Now we've actually shot ourselves in the foot to the point that we can actually make structural selections this way. When we actually try it out, what we find is that for dozens of structures, when we've done this, we actually can select the candidate. For this is from a crystal structure prediction process. We actually do select the correct structure every time that we've done this, for structure after structure. And we know the neutron structure in this case, the blue one, and we actually get, so we know that we're getting the right structure. And everything else can be rejected with, in this case, greater than 99.5%, 99% confidence. So one of the uses for distance measurements is to monitor the refinement of model structures. So here's a case where we have candidates from a crystal structure prediction process. And when we tried to do a distance measurement between all the candidates and the correct structure and the neutron structure, what we found out is the neutron structure, which we know is correct, actually gave the worst fit of all. And the correct structure wasn't anything very special. It was one of the more poorer structures. And it's not surprising because crystal structure prediction often uses low-level calculations, and so you can understand why they may need to be in need of refinement. So if we do a lattice including structure refinement using cast step software in this case, we end up being able to refine coordinates. And the nice thing I want to point out here is the distance metric allows us to follow the refinement. We actually can see that we've got improvement, and we can see neutron now and the correct structure essentially match in a statistical sense. So distance is actually, if we can measure distance, one of the uses for it is to follow structural refinements. Another application of distance measurements is to compare different experimental methods. So in this case, several authors, including us, have acquired N15 shift tensor data on histidine hydrochloride hydrate. And there's a large single crystal that's known for this, so there's something that we could consider a gold standard that we would compare against. And we can ask the question, which of the methods that are out there are actually giving the best data? So we can compare them all. And in the column here towards the right, we can see we get a distance for all of those. And the single crystal had an error of around 5.5 ppm, and Fireman's Spinal actually matched the data within the error. So we can talk about which methods are better using the distance metric. So in conclusion, I want to say that analysis of chemical shift tensors in the icosahedral representation is the mathematically correct way to compare accuracy of different experimental tensor measurement methods. It's also the correct way to compare tensors from theoretical candidate structures from a crystal structure prediction process or another process with experimental data with the aim of selecting a correct structure. The icosahedral method is also the correct way to do the analysis if you want to refine crystal structures from any source. And presently in my lab we refine structures from X-ray powder, X-ray single crystal, neutron single crystal surprisingly, and theoretical crystal structure predictions. And finally I want to acknowledge the NSF for funding my research.